3.5. And we're talking about the triangle sum theorem. And one thing that's really interesting about the triangle sum theorem is, well, one, we've been talking about polygons, and then we were talking about parallel lines. And now we're talking about triangles. And what's interesting is that it actually has to do, triangle sum theorem has to do with parallel lines. So let's write the parallel postulate. And this might not seem like it has anything to do with triangles, but it turns out that it does. So the parallel postulate tells us that if we're given a point and a line, there is exactly one line through the point parallel to the line. And we'll draw a picture here in just a second. So our parallel postulate says that if we have a point, here's point P, and we have a line, there's line L. There is exactly one, only one single line through P that is parallel to L. Yes.
So, like, what would a question? What kind of question would this be answering?
Well, we'll get to that. So just hang on for just a second, and we'll show how this helps us out. Now, before we go on, I just want to talk a little bit about the parallel postulate, because for a long time, the parallel postulate was one of the postulates. Well, first let's remember what did we say a postulate was? Something we accept as true, we believe is true without proof. So the parallel postulate was one of the postulates that Euclid came up with that has caused, I guess you could say, controversy in mathematics, because there were a lot of people that thought that maybe we should be able to prove the parallel postulate. Maybe it shouldn't be a postulate, it should be a theorem. We should be able to prove it starting from somewhere else. So there was a lot of work to try to prove the parallel postulate, so saying it really shouldn't be a postulate. And then around the turn of the century-ish, some mathematicians said, well, what if we don't accept the parallel postulate? What if we say that there is more than one line parallel to line L through point P? Well, it turns out that when you do that, you come up with different kinds of geometry. So, for example, if we say that there is more than one line through point P that's parallel to line L, we're talking about the geometry that's on the surface of a sphere. So if you think of the Earth, lines that go through the North Pole, they always meet at the North and South Pole. So we call those parallel lines on the surface of the Earth, but they always meet. So there are more than one line through a point that's parallel to another line, because they all go through the North and South Pole. If you say that there are an infinite number of parallel lines through point P that are parallel to line L, then you get a kind of geometry called hyperbolic geometry, and there's an idea that that's the way that space is shaped, that the way that space is curved, you can make an infinite number of lines through point P that are parallel to line L. So the parallel postulate has led to a lot of interesting and different kinds of mathematics. And so it's one of the postulates that we talked about that really led to a lot of different ideas. All right, so our parallel postulate says we have exactly one line in Euclidean geometry on a plane. We have exactly one line through this point that's parallel to line L. I'll write down our triangle sum theorem, which is something that we've all talked about almost since we've started learning anything about geometry. We've said all the angles in the triangle add up to 180. So that's what the triangle sum theorem is, and then we'll go to how the parallel postulate helps us figure out the triangle sum theorem. So, the triangle sum. Triangle sum theorem just tells us that in any triangle, the measures of all the angles add to 180. Excuse me. So we've been using the triangle sum theorem in geometry. You've used triangle sum theorem, like I said, for as long as you've known anything about triangles, really. You know that the angles add up to 180 always in a triangle. So let me show you my demonstration that kind of shows why this works, and then we're actually going to prove the triangle sum theorem. So here's my demonstration. This is in Geometry Sketchpad. So what I've done is I made it so that this red line up here is parallel to the base of the triangle. So no matter what I do to the triangle, that red line stays parallel to the base. I can move the triangle around however I want, and that red line stays parallel to the base. So that's how I constructed this demonstration. Now, what we're going to do is I'm going to take this triangle and I'm going to rotate it around. So let me do this, and now I'm going to rotate this, and I want to do it at 45 degrees at a time. All right, so I've rotated the triangle, this green triangle, around this point. So I've rotated it 45 degrees. Let's rotate it another 45 degrees. So there's another 45 degrees. So now I've rotated from here, rotated around. So we can see that this angle is rotating up to here, and now it's rotated up to here. Now let's rotate it another 45 degrees. Now it's rotated, this angle has rotated here, here, now it's rotated to here. What do you think is going to happen when I rotate this all the way around? What do you think is going to happen to that angle? Anybody have an idea? No ideas? Okay, let's rotate it one more time. What happened to the angle? It became a parallelogram, but this angle right here rotated around to here, then to here, then to here. So now this angle rotated right there. So what do we see about that angle? Doesn't it fit perfectly in there? Yeah. It's perfectly in that little slot. So let me color this triangle a different color. So we'll color it blue. All right. So we rotated this angle around. It rotated around, and it fits right in there. I'm going to do the same thing, but I'm going to rotate the triangle the other direction.
Does it have to be the opposite point?
So yeah, I'm rotating it around this point. So let's transform this. We're going to rotate, and I want a minus sign there. So we're rotating around the opposite direction. So now this angle rotated up to here. We'll rotate it again. So the angle rotates to here. Rotate it one more time. Now it's rotated from here to here to here. What do you think is going to happen to that angle? It's going to match. You think it's going to fit perfectly right in there?
Yep.
All right, so let's rotate it one more time. All right, there it is, fitting
Blue.
right in there. So let's color that one
Blue.
blue. All right. So what we see here is now I've rotated the triangle around twice. This angle matches up right here, and this angle rotated around and matches up right there. What do all three of these angles have to add up to? 180, because they make a line, right? Well, this is one angle of the triangle. This is another angle of the triangle. And this is the third angle of the triangle. So we've done this little demonstration that shows that the three angles match up to make a straight line. So that was the point of the demonstration, is to show how that works. Now we're going to write out a proof that just kind of mirrors what we've done here. So let's go back to our page. So now we're going to prove this. And I think it's really cool that after just a couple of months in geometry, we are now able, just with a few simple tools, to prove something that we've believed is true for almost our entire lives. So, we're going to draw a triangle here. And we'll label the triangle ABC. And we'll call this angle 1, this angle 3, and this angle 2. So we are given, all we're given is triangle ABC. And we want to prove that measure of angle 1 plus a measure of angle 2 plus a measure of angle 3 equals 180 degrees. Yes? All right, so here's how the parallel postulate helps us. So let's write our statements and our proof. Our reason. And I wanted to make this should just be a curve, not a... All right. And these are our reasons. All right, so here is how the parallel postulate helps us. I am going to draw, listen up guys, I'm going to construct a line L through point C that's parallel to segment AB. Yes.
Would one be considered a two segments?
It depends on the triangle. It could be. It could be.
Like right there, would that be obtuse?
Probably this would be obtuse,
It's $2.
the way I drew
Is
it.
it obtuse?
Yes.
It doesn't matter. For the proof, it doesn't matter.
You just said the way I
All
drew
right.
it was obtuse.
So, listen up. So,
Measure.
so I'm drawing line L through point C. Listen up, guys. I'm drawing line L through point C parallel to segment AB. So I'm going to say L is parallel to AB. What tells me I can draw a line through point C that's parallel to AB? What did we just talk about? What was our postulate? What did we start out with? The parallel postulate. The parallel postulate says that there's exactly one line through point P that's parallel to another line. The parallel postulate tells me I can construct a line through point C that's parallel to the base of the triangle. That is the parallel postulate. Now I'm going to draw in some more angles. This is angle 4, and this is angle 5. Now I'm going to say, just like we did for on our demonstration, the measure of angle 1 plus the measure of angle 4 plus the measure of angle 5 equals 180 degrees. When we did our demonstration, what did we say the reason was that they added up to 180 degrees? What did they make? We said it when we did our demonstration. What do they all make when we add them all together? They make a straight line, right? So we're going to say angles form a line. So those three angles form a line. Now we're going to use what we know about parallel lines. Line L is parallel to segment AB. What kind of angles are angle 4 and angle 2 for those parallel lines? What kind of angles are those? If this line is parallel to line L and this side of the triangle is our transversal, what kind of angles are angle 2 and 4? Are they between the parallel lines or outside the parallel lines? They're between, so they're interior angles. Are they on the same side or opposite side of the transversal? Opposite. So what do we call two angles that are on opposite sides of the transversal inside the parallel lines? They're alternate interior angles. What do we know about alternate interior angles? They're congruent. This is just like our opener. What about angle 5 and angle 3? Same thing. They are also alternate interior angles. So now my next step is going to be to say that measure of angle 4 equals the measure of angle 2, and the measure of angle 5 equals the measure of angle 3, because they are alternate interior angles. And now, what I'm going to do is take measure of angle 2, like this, and I'm going to put it right here for measure of angle 4 because they're the same. And I'm going to take measure of angle 3 and put it right here for measure of angle 5 because they're the same, and say that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180. And what I've done is substitute measure of angle 2 for measure of angle 4 and measure of angle 3 for measure of angle 5. So my region is substitution. And we're done. So in 4 steps, we proved that all the angles in the triangle add up to 180 degrees. And what helped us do that was the parallel postulate. We constructed this parallel line, and that let us use these alternate interior angles and say that they're congruent. No, the parallel postulate is what tells us that we can make a line that's parallel to another line. So if they were given, it would say line L is parallel to segment AB. Then it would be good.
Wait. Okay.
Questions? All right. So I think it's pretty cool that we're able now to prove something that we've accepted as true for almost all of our lives. So to me, that's a pretty cool thing. It's nice to know why the things you believe are true are true. Yes.
Why is it substitution?
Because I took measure of angle 4 and measure of angle 2 are the same. So I substituted measure of angle 2 right there.
Oh,
Measure of angle 5 and measure of angle 3 are the same. So I substituted measure of angle 3 right there. There are not proofs on the quiz, but there are proofs on the test. All right, we have one more thing to talk about today. That's kind of related. The exterior angle theorem. All right, guys, so stop talking, please. Exterior angle theorem tells us, and we'll draw a picture after we write our theorem so we see what this means. The measure of an exterior angle of a triangle is equal to the sum of the remote interior angles. It sounds kind of complicated, but it really is not. So let's draw a picture. Here's my triangle. And I'm just going to extend this out. And we'll call it angle ABC. And I'm going to call that angle 4, that angle 3, that angle 1, and angle 2. Angle 4 is an exterior angle. So angle 4 is our exterior angle. Angle 1 and angle 2 are remote interior angles.
What's remote is that? What's remote?
Just, we'll say in just a second. So angle 1 and angle 2 are remote interior angles. So angle 4 is our exterior angle. Exterior just means outside. It's outside the triangle. Remote just means far away from. So angle 1 and 2 are far away from angle 4, basically. So they're clear on the opposite side of the triangle from angle 4. So we call them remote interior angles. So this is what, so angle 4 is an exterior angle. Angle 1 and angle 2 are the remote interior angles. We're going to do another proof here. It's short, but when we do the proof, we'll see this makes sense. We know why this works already. We already know why this works. So we're going to prove that measure of angle 4 equals a measure of angle 1 plus a measure of angle 2. All right, so here's our proof. So all we're given here is that angle 4 is an exterior angle. That's all we're given. Angle 4 is an exterior angle. Now, what do we know about the measure of angle 3 and the measure of angle 4? They add up to 180. Perfect. So measure of angle 3 plus a measure of angle 4 equals 180. What would be our reason? What kind of angles are there? What do we call two angles that are on the same side of a line? A linear pair. Angle 3 and angle 4 are a linear pair. We know that linear pairs are supplementary, so they add up to 180 degrees. What do we know about the measure of angle 1, 2, and 3? What do they add up to? 180. And what's our reason now? What do we have a reason? Now we know why they add up to 180. What do we call our theorem?
Triangle sum.
Triangle sum. Now, we know that these three added up together equals 180, and these two added together equal 180. So what do we know about these two things? They're the same. They each equal 180, so they have to equal each other. They're the same thing. So I'm going to say that measure of angle 3 plus the measure of angle 4 equals measure of angle 1 plus measure of angle 2 plus a measure of angle 3. And the reason there, I substituted this right here for 180. So let me put that, I'll highlight that. Where's my highlighter? There it is. So I highlight this, and I substitute this right there for 180 degrees. So that's substitution. Now what thing is on both sides of this equation? What angle? Angle 3. So angle 3 is on both sides of that equation. I have an angle 3 here, and I have an angle 3 there. What is it doing on each side of the equation? Adding, subtracting, multiplying, or dividing? It's adding. How do we undo addition? Subtraction. So if I subtract the measure of angle 3 from both sides of this equation, that will get rid of measure of angle 3. We'll subtract and that'll go away. So I end up with the measure of angle 4 equals the measure of angle 1 plus the measure of angle 2. And my reason is subtraction. And I've proved what we were trying to prove. That the measure of angle 4 equals a measure of angle 1 plus a measure of angle 2. And this works because these two have to add up to 180, and all three of these have to add up to 180. So these two added together have to be the same as angle 4. So when you're doing a problem like this that has a remote, an exterior angle, all you have to remember is that these two add up to 180, and all three of these add up to 180. You don't even necessarily need to use the exterior angle theorem. You just use what you already know, that these are a linear pair, so they add up to 180, and all three of these add up to 180. And that will get you your answer if you're working with an exterior angle. All right, any questions on our exterior angle theorem? All right, and this all comes back to what we already knew about triangles, that all the angles add up to 180 inside a triangle. All right.